So now we're going to talk about rationalizing and dividing radicals, and in a way simplifying in general. And we've got the rules, our three no-nos for simplifying radicals. The radicals have to be in simplified form, or if we ask you to simplify it, then they have to satisfy the conditions that they don't violate any of these no-nos. So the first no-no was no perfect square factor under the radical. So here's an example. If I look at this, the square root of 250, is there a perfect square factor? Yes, there is a perfect square factor. 25 goes into 250, and that's a perfect square. So I can rewrite this as the square root of 25 times 10. So you can see that, okay? And now, what's the square root of 25? That's 5, so I can bring this out. I can rewrite this as the square root of 25 times the square root of 10, but it's the same result. The square root of 25 is 5, so that's going to be simplified to be 5 times the square root of 10. And now that's simplified form because there's no perfect square factor under 10. 10 is 5 times 2, and neither one of those are perfect squares. All right, here's another example. The square root of 18, that's the same thing as the square root of perfect square factor 9 times 2. What's the square root of 9? 3, so I can rewrite this. I can take the 9 out. The square root of 9 is 3, and 3 times the square root of 2. Or I could write this as the square root of 9 times the square root of 2, and the square root of 9 is 3. So no perfect square factors under the radical. Those are kind of simple examples, but they should help. The second no-no is no fraction under the radical. Well, remember we used one of our properties that the square root of a quotient is the quotient of the square roots. In other words, the square root of a fraction is a fraction of the square root, so I can make this as 2 square roots. The square root of 7 over the square root of 16. Now we've got rid of the fraction of the radical. And what's the square root of 16? 4, so we're in good shape. So that's our second no-no. Our third no-no is no radical in the denominator of the fraction, and this is where we get into what we call rationalizing the denominator. In other words, we want to multiply this by something that will make this a perfect square. Well, 7 times 7 is 49, so that's a perfect square, so I'm going to multiply the top and the bottom by the square root of 7. Now, what's the square root of 7 over the square root of 7? Well, that's just 1, isn't it? And you can multiply anything by 1. Those are properties of what we call the field of real numbers, and you can multiply anything by 1. It's the identity element, and you'll just get back that same number. So 1 over the square root of 7 times 1 is just still 1 over the square root of 7, so we're multiplying the top and the bottom. And when we do that, on the top we've got the square root of 7, and on the bottom we've got the square root of 7 times the square root of 7. That's the square root of 49, and that's just 7, so we've got the square root of 7 over 7. And you could skip this step if you want, because you know the square root of 7 times the square root of 7, which is the square root of 7 squared, which is square root of 49, which is 7, or just 7. All right? Now we want to do this the easiest way possible. So here's another example. So what's the next perfect square I can make this? Now don't be saying, well, I'm going to multiply it by the square root of 32, because you're going to have some simplification to do, because this really isn't simplified. There's a perfect square factor under here. Sometimes you see them like this. They throw these at you, and this is really not simplified. So we'd have to simplify this first. But if we just want to leave it in this form, what's the next perfect square I can make that? Well, the next perfect square is 64. The square root of 64 is 8. So all I have to do is multiply the top and the bottom by the square root of 2. I don't have to multiply by the square root of 32. Remember, 32 is the same thing as 16 times 2, so it's already got a perfect square factor of 16 in it, so it's not simplified. So you can get away with it with a smaller number. So when we do that, we multiply this. We have on the top 1 times the square root of 2 is the square root of 2. On the bottom, we've got the square root of 2 times 32 is 64, which is just 8. So it's just the square root of 2 all over 8. So those are your three no-nos, and those are kind of simple examples. So I hope that kind of makes sense. Sometimes you'll see situations where we need a perfect fifth root So you have to kind of find your fifth powers, which are kind of tricky. So sometimes you run into something like that. So this is a problem. It's kind of challenging too for this. So I think I should probably help you out with this one. If you run into this. Here's an example. Eight over the fifth root of 12. So what I would do is I would factor this first, so I would have it 8 over the fifth root, and I'd find the prime factors of 12. So if I've got 12 over here, okay, I get divided by 2. 2 goes into there 6 times. 2 goes in there 3 times. So the prime factors are 2 times 2 times 3. Now what I need is I need 5 2's to have a perfect fifth root. 5 2's. Because 2 to the fifth is fifth root of 2 to the fifth. You know this. The fifth root of 2 to the fifth is just going to be 2. All right? And you can work this out. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So the fifth root of 32 is 2, because 2 to the fifth equals 32. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So I need 5 2's under here. So really what I have to multiply is by 3 2's. So I can multiply the top and the bottom by the fifth root of 2 times 2 times 2, which is just 8. But I can write it as those 3 2's. Okay, now when you do that, you have 8 and the fifth root, and that's 2 times 2 times 2, which is 8. And on the bottom, you've got the fifth root, and notice I've got 1, 2, 3, 4, 5 2's, which is 2 to the fifth, times 3. Okay? Now what's the fifth root of 2 to the fifth? Well, the fifth root of 2 to the fifth is just 2, so 2 times the fifth root of 3. And now I need, so now I've got 8, 2 goes into 8 4 times, so I can simplify this a little bit. 4 times the fifth root of 8 all over, that was nice, the fifth root of 3, but now I've got to rationalize this, so I need 4 more 3's, so now I'm going to have to multiply by the fifth root of 3 times 3 times 3 times 3 all over the fifth root of 3 times 3 times 3 times 3. And now I end up with 4 times the fifth root of 8 times the fifth root of 3 times 3 is 9, times 3 is 27, times 3 is 81. All over, and that's 1, 2, 3, 4, 5, 3, so that's just the fifth root of 3 to the fifth, which is just 3. So now I've got 4 times the fifth root of 8 times 81, because I couldn't put those both under the same radical, all over, and the fifth root of 3 to the fifth is just 3. And what's 8 times 81? Well, 8 times 1 is 8. 8 times 8 is 64. Right? So it's 648 all over 3. So that was kind of a pretty challenging problem. So there might be a quicker way to do this, but I didn't really want to mess with 12. So I kind of separated it up. You could have maybe combined these and didn't done your 5/3 over here, but it would have been a little bit longer. So I did it in stages, but I hope that should make sense.